Welcome back to Engineering 255. This is the video of the Chapter 7, Internal Forces. In the previous chapter, we're looking at the structural analysis. We introduced two different methods to help us to understand what is the loading on each one of the member of a frame, a truss, or a machine. Now, we are going to extend these two methods to see how we can use these methods to find out internally what is the force and moment inside of the member. So the main method we're going to use is going to be the method of the section, but we're going to carry the same way as we learned before to understand the supporting force, and we are going to cut the section to find out the internal force for each one of the member. And that is the objectives of this chapter. So we wanted to review the method of the section, which simply you cut the member by imaginary. But this time we're going to cut the member from the beginning to the end. And most of the time it will be just the member of single member instead of multiple member. And we're going to mainly look at the two-dimensional situation, and the loading that we were trying to find out are the normal force, the shear force, and also the bending moment. These are the three internal loading that we're trying to find out. The application for this analysis are the following. So this example that you can see is a bridge. When you look at the bridge, they're not normally uniform design. They were designed with a long span, but at a certain place when you connect to the support and goes down to the bottom of the river, it will be a thicker structure. But in the middle between two support, you can see over here is thinner as opposed to where you connect to the support. There must be a reason, and one of the reasons is that we try to save as much material as we could, but you also wanted to make sure that the structure is safe. To analyze whether the bridge or this kind of structure is safe or not is to understand what are the loading actually apply to that part of the bridge. So we need to find out these forces so we can analyze how to design this supporting system. This is another example. You can see there's a fixed column support a rectangular billboard. So this billboard is right here, and this post or this column is the one that we need to design. We want to make sure this column is strong enough to support this, right? And normally you can see the bottom part is thicker than the upper part. There must be a reason that we make the bottom part to be thicker, and why is that? And we can analyze by looking at the analysis we're going to introduce in this chapter. So before we start to do the analysis, let's understand some of the terminology. What are the internal forces? When you see there's a structure like this and we apply a force at the point of B with a 6,000 Newton, and at the end, which is the point D, we also have this one, which is called the moment, right? By looking at the unit up here, you see there is a moment at here. But what we want to understand is that in each part of the structure, are they going to have the same amount of the loading or not? Meaning internally, do they have the same amount of the forces and the moment? And the answer is going to be no. How do we analyze this? to know what actually loading internally, we first need to understand what are the supporting force at these two support point A and D. And we can use the previous chapter method to analyze how much A and D are. And once we understand those two loading point, and we can use the method of the section by cutting the member at some point, and we want to analyze what are the internal forces applied at a particular point. At this example here, we're looking at a point at B, so which is right at the force that you apply to the point. Would the loading just right before the B or right after the B be the same? The answer is no. And to analyze that, let's just assume that you cut the member just right before the B. And you can assume at point when you cut the section at point number B, you are going to have some reaction forces, right? When you cut something out and you're going to put the reaction forces, and these reaction forces has three different kinds. And the first one is this one here, the ends of B. This is what we call the normal force. So the normal force is going to be the force perpendicular to the cutting face where you cut down of this point B. So the normal to that cross section is going to be the normal force of B. Along the cutting face, there is another force, what we call the shear force. Shear force is the force that is parallel to the applied surfaces. So when you cut this one, the applied surface is the perpendicular surfaces, and the force that is parallel to that is what we call the shear force. So V sub B is the shear force. There also another possible things will come out, which is the moment. So this moment is this moment right here. This is what we call the bending moment. That is to quantify how much of the object tends to bend because of the force. So this bending moment is what we put M of B at here. Now, one of the things is very important is the direction. And we are going to see how we define positive and negative on these things. So this side kind of summarize what we just talked about. You have a normal force. This is the actual force, which is along the direction of your component. So this could be a beam, this could be a rod, and the force that is along this direction, which is the actual direction, is what we call the normal force, and we use N to represent it. Shear force is acting along the surface, and the bending moment is the thing trying to make it bend. When you cut things on the right, on the left, that should be equal. That's what we call the Newton's third law. So if you have this force going to the right and the other side, and it's going to the left. Now, that's very important to identify the direction or the sign convention of the three different things. The first one, N, is the normal force. It's a positive if it creates tension to the component that you're looking at, such as this is the one piece here. And if you apply tension, that is going to be the force going outwards, and that is what we define as the positive. But when you cut one thing into two pieces, like cut this one into two pieces, we're going to assume On the left hand side, it go outwards of the left hand side is going to be positive. If you look on the right hand side, then the force to the left is the positive direction. So always if it's create a tension to the object, is the end that is positive. For the shear force, shear force is the force that try to make the part to rotate clockwise. So if you think about this as a one piece and you cut this one into half, on the left hand side, this is the left hand side half, this shear force will make this part turn clockwise, right? So this shear force in this direction is going to be positive. On the right hand side part, then clockwise is going to turn in this way. So on the left hand side, when you apply a shear force, it has to go up. That is the positive direction. So when you cut the member, you can analyze the member from the left or from the right, but you have to know which direction is positive, depends on which side you're looking at. For the bending moment will be positive when you make this one bend upwards. So this is what we define as a positive direction. On the right hand side, this is going to be the positive direction because they tend to make things rotate upwards. So when you make things rotate upwards, that's the direction that is defined as the positive bending moment. Now, let's look at what is the step to determine the internal forces. The first step is that you're going to cut the piece, take an imaginary cut. What you wanted to determine the internal forces. So you have to make sure what is the desired point, and you cut that piece at that point that you try to determine. And if you don't know the supporting reaction, you should use the entire structure free body diagram to find out the internal, to find out the supporting force. This normally is the first step. When you look at the structure, normally they would not give you the supporting reactions. That you have to use the step 2 to draw the entire body and find out the supporting reaction at the joint. And once you identify which point that you're going to cut and you cut it, you're going to have two pieces. So for each one of the piece, depends on which one that you wanted to use, and you draw the N, the V, and N. And remember, N is the force created tension. V is the force that tends to make the part rotate clockwise. N is the bending moment will make the piece bend upwards. And then you use the equation of equilibrium of the free body diagram to solve for a non-internal loads. Let's look at an example to explain how this process is applied. Here we look at an example that we have internal force. We wanted to find out internal force at C, this point right here. And you can see the structure has a distributed load right here on the left of the point A. You have pin on the right hand side. So before we cut this object, we normally need to determine what is the reaction force at a different point, right? So you wanted to make sure that you can find out the internal force, supporting force, not internal force. The supporting force at the point of A, where the A is a roller, so the point A, you have only the up force at this point. For the points B, you have two forces. Then is one go to the up and the other one goes to horizontal. So one is the X component, one is the Y component. And if you look at the structure, you also need to replace this distributed load by a resultant force at a central point where you are creating no moment to the left or right of this distributed load. So how do you find out the total load of this? Well, you have 6 feet at here. There's a 3 kip. Kip represent 1,000 pounds. So the 3,000 pounds per feet, and you use 3,000 times 6. That is the total load that you come out from this distributed load. And because this is rectangular, so this will be just right at the middle of the 6 feet. That will be the point that can represent the distributed load here. So we put the free body diagram by what we identify. We have this distributed load right here. We have AY at here. We have BY and BX at here. Now the direction is arbitrary. This one make it go down, but you need to know that this direction is arbitrary, and once you find a solution, that direction, the sign will tell you the correct direction of the load. So how do you analyze this? Well, you use summation f of x, summation f of y, or summation moment. Then you can find out the solution where 3 unknown, ay, by, and bx. If you take summation f of x, there's only bx in that direction, so bx is equal to 0. That's really helpful, and we don't need to worry about this one. This is not going to affect anything at here. The next thing we do is that we can use summation moment, and we need to have a reference point. If you use reference point of A, which is this one, AY is not going to create any of the moment, and you have 18 kips to create a moment that is counterclockwise. The BY is going to create a moment which is clockwise. These two should be equal. So the distance for the left hand side is the 3 feet. The distance of the right hand side is the 9 feet. So you use this equation, you can find out what the BY is, which is 6,000 pounds, and that's 6 kips. Now the last thing we need to find out is the AY, and it's very simple because this 18 going down, this BY 6 going down, and it should be equal to the AY going up. So you sum these two, that should be the AY. So the AY should be 18 plus 6, that should be 24 kips. Okay, 24. Okay. So what do you do after you find that? Well, our purpose is to find out what is the internal force at this point of C. So we have to cut the C to find out the solution. When you cut this one here, and we have two parts. We have the part on the left, and we have part on the right. So in this example, we use part on the right, which is this one here. We know the BY is 6 kip going down. There's no BX. And when you cut this one, you are going to put 3 different loading at the cross section that you cut it. This V sub C is the shear force, and we say V sub C is positive if it make the things rotate clockwise. So when you draw this one, this actually is a negative direction. And N sub C is going to the direction that goes to the left will be the tension force. So this one actually is also a negative direction. This moment of the C is the positive direction because it tends to make these things rotate upwards. But it doesn't really matter because you just need to know what is the value of this, and so you can find out the solution. And to find out the value is the same, you use the equation of equilibrium. We look at the x direction. N sub c is the only force on the x direction, so N sub c equal to 0. So we find out the normal force at the point C is going to be 0. The second one you do is that you can sum the F at the y direction. So V sub C plus 6 kip equal to 0. You got V sub C is equal to negative 6 kips. That simply tells you this V sub C should be in the direction in this direction. That is the correct direction. And this amount is going to be 6 kips. The summation moment can tell us what is the moment of the C equal to. And we are not going to, well, and you can pick the point C or you can pick the point of B. If you pick the point of B, then this N sub C and V sub C is not create any moment, and our summation moment is going to be moment of the C plus the 6 kips times 4.5. And that is what we see at here. Now the direction, let's look at the direction. This one tends to make it rotate in clockwise. This one that we mark at here is also clockwise. So when you do the calculation, if you want to sum these two, you should have the 6 times 4.5 plus M sub C equal to 0. And that's how you find N sub C. Over here, well, this should not, so this one's supposed to go the other way. That will be the correct direction, I think. So this arrowhead should be the other direction. Because we normally define the counterclockwise as the positive direction, so then you put negative because this one make it go clockwise, and this is also the clockwise M sub C, and that will give you N sub C is equal to 27 kips feet. So this gives us the answer if we wanted to know how much of the force acting on the point of C. And the answer is you have a shear force, which is a 6 kips, and this force is going up. And you also have a moment at point of C. This moment is going to be the moment that is going to be counterclockwise, and that's 27 kips feet. So in summary, the first section of this chapter is to introduce the 3 different internal forces that you need to know. And these 3 different internal forces are the N, which represent the N represent the normal force, and you have the V represent the shear force, and the M represent the bending moment. And when you solve this, you just cut the point that you are interested, and you use the same way to find out the equilibrium equation, so you can determine the amount of the internal forces. And that's what you need to do. In the next video, we're going to introduce some more general case, what happened if we wanted to know each one of the point, and then we have to do more calculation to understand how the loading can change the internal loading as well. That's it for this video.